So this talk, I think on the syllabus was listed as restricted model of quantum computing 1 or 2, but I decided to give it a slightly different name, which is, as you'll see, I hope to convince you that it's a related name. And I was debating whether or not to put a question mark. I decided against it, but you can judge for yourselves. So it's about quantum computing before fault tolerance, and so I want to first give you some context, and then for most of this talk, I'll talk about some specific research project in that area. But first, I want to give you some context. So first of all, we talked about some of the evidence for quantum computers being better than classical computers at solving certain problems. We talked about briefly the algorithm, Shor's algorithm, as well as efficient simulation of quantum mechanical systems. And there are many others that I could list here, but I didn't. Like, for example, the listed problems in knot theory and graph reachability problems and so on. So these are problems where the quantum algorithms beat the best classical algorithms that we know. But then there's also another class of problems which you can think of as like sampling problems. And we'll talk more about those this afternoon. And here you have some quantum circuit, and you apply it to some basis state, and then you measure all the qubits in a computational basis. And under some conjectures, one can show that it is hard classically to sample from the same probability distribution. So we'll talk more about those sorts of arguments this afternoon. Another form of evidence are these provable speedups relative to an oracle. So these are speedups like what we talked about on Monday, such as the Bernstein-Vazirani speedup, or the speedup from Simon's problem. So those are problems where part of the input is this black box. And so in a setting where you have this black box oracle, you can actually prove that the quantum is better than classical. Okay. So these are sort of the off-the-shelf quantum algorithms, or something. And what we also talked about, or Dorit talked about, was the need for quantum error correction. And the need for quantum error correction stems from the fact that if you build a quantum computer, then no matter how you build it, there will be error. And at some level, you should think of errors as occurring randomly at all locations in a circuit, in a quantum circuit. That's some kind of toy model of errors. And so if you have like n qubits and the circuit depth is d, you should think of the circuit depth as just being the width of this picture for now. We'll talk more about it later. Then sort of the number of errors that occur, if you have like an error rate epsilon, the number of errors that occur is like epsilon times n times d. And so if you're not doing any error correction, then you need to, naively you would need either very short depth or very few qubits. Now very few qubits is not as interesting as very short depth, because very few qubits, let's say you have, I don't know, 10 or 15 qubits, then you can simulate that on your classical computer. And we'll talk more about short depth computations and what you can do with them. Okay, so the quantum computer is subject to noise, and we heard about how error correction can overcome noise by encoding a logical qubit redundantly into many physical qubits. So this is some kind of picture from this paper by Gambetta, and Stefan, which illustrates some 25 qubit error correction code. And so you encode a qubit into many physical qubits, and then you actively perform error correction, and in this way you perform fault-tolerant quantum computation. But one thing that I think was not discussed in this course so far is that the overhead for fault-tolerant quantum computing is asymptotically small. So in other words, it could be, for example, using certain recent proposals, it could be as small as constant. So if you take a computation and want to encode it and do it fault-tolerantly, it could be that the overhead is constant. But at least or at most, it's polylogarithmic in the size of the circuit. So we know that for sure. So asymptotically, the overhead is small, but if you ask about what are the actual numbers, then they become, well, they're quite large. So I think the best estimates, what I've heard recently is that the best estimates, the most optimistic estimates are hundreds to thousands of physical qubits per logical qubit. So you can imagine that in a world where quantum computers are just now becoming a reality, it would be challenging to start by encoding one logical qubit into 1,000 physical qubits and move from there. Okay, so that's kind of the situation we're in, and machines do now exist. So this is a screenshot from the IBM Q Experience, which is a website where you can go and, well, it's not just a website. I mean, there's hardware that is housed at IBM, and which you can go on this website and for free you can run experiments on these quantum computers that are housed at IBM. So these are, there's a 16-qubit machine. At the top there it's pictured, and it shows you all the connectivities and the error rates of the qubits and so on. And on the bottom is a 5-qubit machine. So these are small devices for now. But in the future, we expect that future quantum computers will become too large to simulate on a classical computer. And that sort of threshold of how big is too large, it's not so much bigger than what we have now. So maybe it's 50, maybe it's 80 qubits, something like that. But these devices are subject to noise, and so we can't run the off-the-shelf quantum algorithms without incurring errors. So what does it mean to have a quantum computer that is noisy, but still too big to simulate? Like, what do you do with that? And that's sort of the question of what to do with quantum computers before fault tolerance. And the reason I want to give you this context is because this is something that our field is sort of grappling with, and that has come to, I think, has maybe come too quickly for those of us who are theorists, because we have been thinking more about algorithms for fault on quantum computers. And so, okay, I know you can't read this. I just want to show you some things that have been happening. So this is a conference we had at IBM on this topic. It's called Approximate Quantum Computing for Advantaged Applications. So this conference was in December, and you can view all the talks as well as a panel discussion online if you're interested in this topic. Yeah.
Sorry, just a question on how roughly we got up to needing hundreds or thousands of qubits to correct errors. Was that because we had a 9-bit code?
That's right.
That was only for
That's right. So there are codes which only require a small number of qubits to input them, but then you require many additional qubits to implement gates, and so sorry, go ahead, Dory.
I think the right answer is that 9-qubit code gives you some protection from errors. Still, you will have some probability, so you will be able to correct one error. But if you have 2 errors, which you have some probability to have, then you won't be able. Then the whole thing is corrected. So you have to deal with that.
You get up to 1,000 if you're like to deal with a realistic number of errors that you might have.
You have to somehow do it either in a hierarchical manner or do something so that you will be able to handle more errors.
Yeah, it's not just that you take one of these simple codes for every qubit and that's it. There's also, yeah. Anyways, so if you are interested in this area, there's these talks from this conference, which just happened recently. The other thing I would point you to is this paper by John Preskill. So he coined this term, the NISQ era, noisy intermediate scale quantum computing, which is, and this is a lecture he gave actually at the same time as our conference, but at a different conference. Anyways, maybe it was the day before our conference. In any case, this is all sort of happened in the last few months. So what is the question for quantum computing before fault tolerance? So basically, I think the sort of relevant question is, what can we do with limited or no error correction using short depth circuits over a gate set that is determined by the architecture of the devices that are available? And so now if you just look at like what are the answers to this question that are present in the literature, there's like a few proposals. One of them is to do things like heuristic algorithms. And we'll talk about a couple of these this afternoon. These are algorithms that don't have performance guarantees. guarantees. That's what it means to be heuristic. So, it's hard to judge them without performance guarantees and without being able to try them out on large devices and compare with classical. But some of them have some interesting features, and the hope here is that one could design heuristic algorithms that you can't classically simulate, and then that's some kind of advantage, and then the hope is to use that for some practical purpose. And these are being used for quantum chemistry and proposed for optimization of machine learning. Okay. So we talked a little bit about the hard sampling tasks, and there are some proposals to use those hard sampling tasks with near-term quantum computers. Finally, it's very sensible, obviously, to use small quantum computers to validate and verify and try out small code and things like this. So these are some of the ideas, but I think that I would advocate the point of view that, one way to make progress or to understand what to do is to address broader questions in algorithms and complexity that have to do with restricted models of quantum computing. Because what we have with these near-term devices are devices where the hardware imposes, pretty strict limitations on what you can do, and then we're asking, how can you still eke out a quantum advantage in that restricted setting? So, this is a sort of age-old question that has already led to many of the current proposals for what to do with near-term quantum computers. Which restricted forms of quantum computing can be more powerful than classical, and which are classically simulable. And so that's an area that I think is particularly relevant nowadays. Okay, so then with that preface, I want to now go into this more specific portion, which will talk about this quantum advantage with shallow circuits, which is sort of a contribution to this area that we made last year. Okay. Are there any further questions about the first part? Okay. Okay, so first I want to just put things into perspective. So we have all this evidence for quantum advantage in computation, and now I want to poke holes in all of these things. Just to take a skeptic's view. So if I were to take a skeptic's view, I might say, well, the speedups for, speedups like Schur's algorithm or simulation of Hamiltonian dynamics, they would disappear if the classical algorithms could be improved. So we can't prove that they're speedups, in other words. For sampling from these hard classical distributions, well, sampling from those distributions is only hard classically assuming some conjectures, both complexity theoretic conjectures that we believe, but also some less well-studied conjectures that maybe we believe and maybe they're not true. Finally, these provable speedups relative to an oracle, well, oracles don't exist in the real world, and so you can ask, how relevant are they? Okay, so what I want to describe then in the remainder is a provable and non-oracular speedup, although it's very modest speedup and it's kind of in a slightly different setting than I'll explain. But it's actually also attained by constant depth quantum circuits in a 2D architecture, so perhaps more relevant to what's being, perhaps more relevant to the types of architectures that are available today. Okay, so I want to talk first about circuit depth. So circuit depth is the number of time steps in the computation allowing for parallel gates. So what do I mean by allowing for parallel gates? So I'm going to allow you to do parallel gates when the gates act on disjoint qubits. Okay, so they don't overlap. So here I can do these two gates in parallel because they act on 1 and 2 and 2 and 3 and 4. That's one time step. Likewise here, you see this gate here, it's maybe not clear from the drawing, but it acts on this qubit and that qubit. And these two gates act on these qubits, so I can perform all those gates in parallel. That's time step 2. And then likewise, so this is a depth 3 circuit. Okay. So then, why should we care about constant depth quantum circuits? So I already mentioned, well, first of all, you should think about what is constant depth? It's constant time parallel quantum computing. That's what it is. Okay? And we're only going to be talking about gates composed of, say, 1 and 2 qubit gates. Or sorry, circuits composed of 1 and 2 qubit gates. So we talked about, maybe it's relevant to near-term quantum computers, although it's not like, you have to be a little bit careful here, because a near-term quantum computer, without error correction, you really just have an upper bound on the size of the circuit that you can perform without having any error. So it's not like you can increase the number of qubits while keeping the depth constant and still perform the circuit perfectly in a near-term quantum computer. You wouldn't be able to do that. But it's closer to what you can do with a near-term quantum computer. So there are a few things that are known about the structure of constant depth quantum circuits. And actually, one of the things on this list we'll talk about, actually you're going to do on the homework. The fact that depth 2 quantum circuits can be simulated efficiently classically. The rest of them, maybe I won't comment on. We're going to be interested in what is the computational power of these constant depth circuits. And later today, we're going to talk about this very important Cherhov-DiVincenzo result, which shows that assuming the polynomial hierarchy doesn't collapse, which is strongly believed in classical complexity theory, you cannot efficiently sample from the output distribution of a constant depth quantum circuit, at least exactly sample. So we'll talk more about that this afternoon. But there is some kind of evidence from this and later work that constant depth circuits may be able to sample distributions that you can't sample from using a polynomial time classical computation. So there's evidence for that. So there's a big question, which is, can they solve a problem that polynomial time classical computers can't? And we sort of have some evidence that maybe they would be able to. But we can't really answer that question because this would sort of, depending on how you instantiate this question or make it more specific, if we ask for a decision problem, this would separate, BQP from BPP, and we don't expect to be able to prove that. Oh, that's right. Yeah, okay.
Maybe,
So
maybe it's worth saying that if you have a constant depth quantum circuit and you just want to know the answer in 1 bit, then it's easy to simulate. I don't know if you
yeah, actually, that's on the exercises as well. So you will prove that's right. So if you take a decision problem and you imagine solving it by taking a constant depth circuit and measuring 1 output bit, then that whole procedure, the quantum procedure, can be simulated actually with a constant size classical circuit. So you're not going to be able to separate constant depth quantum from anything using that argument. And yeah, you'll also show on the homework that if a constant depth circuit computes a function, then you can compute the same function in classical constant depth. So we have to be a little bit careful about the sorts of problems we need. Okay, but here, so I want to consider this smaller question: can constant depth quantum circuits solve a problem that constant depth classical circuits can't? And given what I just said, we have to be careful about what kind of problem we're going to be considering.
Algorithms like Grover or Short would actually move.
Well, sure, you need log depth, and Grover. I guess it depends what Grover, you have an oracle, so it's yeah. Yeah. It's sort of an open question whether or not what you can do with log depth circuits with classical assistance. I forget exactly how Joseph has asked this question about using log depth circuits to simulate. I forget how the question is phrased, but I can point you to it afterwards. Okay, so that's kind of what we show is we prove that there is a problem, it's a linear algebra problem that constant depth quantum circuits can solve, and then we prove that constant depth classical circuits can't solve the problem. And actually, the problem really can be viewed as a non-oracular version of something we already saw on Monday, which is the Bernstein-Bazarani problem. So I want to just remind you of how that worked. So that was, remember, an oracular problem. And here's just the reminder. Okay, so actually, I think on Monday we drew the oracle in a different way, like had two inputs, and then you were XORing into the second one. But one of the homework problems was to show that using that oracle, you can implement this oracle, where the function is computed into the phase of a basis vector. Okay, so I would like to think of the oracle as doing this. Okay. So here you have an oracle and an axon on a state x. It implies a phase -1 to the s dot x, where s is a secret bit string. So there's a linear function, s dot x mod 2, and it's hidden inside the oracle. And we want to find its parameterization. That's the goal. We want to find s, the secret. And what we saw on Monday is that there's a simple quantum algorithm which I can just write in this way, as you just apply Hadamard's solid qubits, you apply the oracle, and you apply Hadamard's, and that gives you the secret. That's the whole algorithm. Okay? That's one query. And then we know that a classical algorithm needs n queries just by information theory. So that was a review of what we talked about on Monday. So now, what does it mean to make this non-oracular? It means that, like, we're going to try to hide a linear function, but we're going to hide it in something that's not an oracle, right? So where can we hide a linear function? Yeah.
Are S and Z the same thing here? Could you just?
Oh yeah. Where did I put Z? Oh, you're right. Yeah, I changed it to S because I knew that we used S on Monday, but then I forgot to change it here. Yeah, it should be S there. Thank you. Okay. So where else can we hide a linear function? So I'm going to tell you what we did. Okay. So we're going to hide it in a quadratic function, quadratic form. Okay. So this is the ingredients. So we're going to start with a symmetric binary matrix. So it's n by n, and the entries are 0 and 1. And we're going to define its kernel mod 2. Okay, so that's the bit string x, such that ax is 0 mod 2. And then we're going to define a quadratic form, which takes as input a bit string x, and it just computes x transpose ax mod 4. So there's something funny going on with the mod 2 and the mod 4, but for the moment, just like ignore that, just for a second. Now, and I want to just ask you a question, okay? So imagine everything is like just real variables. So the matrix is real and the vectors are real, okay? So if everything is real, suppose now I take this quadratic form x transpose ax, and now I look at its values when I restrict to vectors x in its kernel. So what happens? It's 0, right? So this is like massive simplification of the quadratic form down to 0, a constant function. Okay? But now I have this like mod 2 and the mod 4, and it's not quite the same. But there's still a massive simplification if I look at q of x on the kernel. Okay? And so now I want to show you that in fact what happens in this case with the mod 2 and the mod 4 is that in the kernel it's a linear function. Okay, so it's simplified from quadratic to linear instead of from quadratic to 0. Okay, so I want to just show you this is like a couple lines of math. Yeah, so I'll do that on the board. So I mean, the point of this obviously is that that's the hidden linear function inside the quadratic function. Right? I said we were going to hide a function, and there it is. All right. So I need one little thing. Yes. So I claim that this is true for all x in the kernel, and y can just be an arbitrary bit string. Okay, so it's the fact that q is linear is going to follow basically straightforwardly from this. Okay, so how do we prove that? So we need to be a little bit careful. So here the addition is mod 4, and here the addition is mod 2. Okay, so the first thing we're going to do is just use this little identity, which is that if I take x plus y like mod 2, I can also write that as x plus y plus 2xy all mod 4. So how do you check that? So this is, by the way, these are vectors, right? This is a bit string. And so here, this is all entry-wise, right? So I'm taking the entry-wise product and the entry-wise sum and so on, okay? But just imagine for the moment that I'm just looking at one of the entries. So now x and y are bits, okay? So then if they're 0 and 0, then I get that the sum is 0, which is the same as the x one. If they're 1 and 1, then I get that the sum is 4, and then I take mod 4, so I get 0, which is the same as the x one. And if they're 0 and 1, then this term is 0, and then I just get the 1, which is the same as the x one. Okay, so this is just an identity. And so then I can use this to write q of x plus y, which is x plus y plus 2xy transpose a x plus y. That's that guy. And now, so I can identify the terms which give me q of x and q of y. So those are the x and the y term. And then I have to argue that all the other terms go away if I look at size x and kernel. So okay, so I claim that if I write this expression out and I collect all the terms, what I get is q of x from the xx term, q of y from the yy term, I get 2 y transpose ax from the cross terms between y and x, and then I get a bunch of terms with 4s in front of them, which are just 0 because I'm taking things mod 4. Now this term, the y transpose ax, when x is in the kernel, that's 0. Okay? So, because I have a 2 in front, it's important that I have a 2 here. It's in the kernel mod 2, which means that ax is 2 or 0. Like every entry of ax is 2 or 0. So when I multiply by this 2, it's now 0 mod 4. Okay? So that's why these terms go away for x in the kernel, and this term just goes away all of them. Okay? So that's this little claim. And now, oh, I shouldn't. Let's see. Well, I think I can just write at the very top, and can you still see it? Okay. So I want to show now this fact that q of x. I want to show that it's 2z transpose x for x in the kernel. And how am I going to do that? So first of all, I'm going to use this claim on like x and x. Okay, so q of x plus x, which is q of 0. Okay, so q of x plus x is by definition q of 0, but if I plug in 0 into the definition of q, of course that's 0. But this is q of x times 2, right, for x in the kernel. I just use this formula, right? It's twice q of x. So what this says is that if I look at the kernel, q of x, and this is mod 4, right, this whole formula. So what it says is that q of x is in the set 0, 2, whenever x is in the kernel. Right? So it's either 0 or 2. So that's the first thing. But now I can just define, so then I can just define a function like L of x, which is just q of x over 2. Okay? Because now that this is 0, 1 value. And this equation says it's linear. Okay. So we're done. It says it's a linear mod 2, like L of x plus y. L of x plus L of y. Alright, so that's so you can see this is not hard proof. It's just what I wrote.
How does these depend on the matrix A?
Yeah, well, how does it depend on matrix A? It depends. Yeah, so that's the second part of this, which I actually I did want to actually say this. So let me say one more thing about Z, which is that it is actually important that Z is not unique. So let me write that over here.
Because of what we said before.
Yeah, that's right. So I said before that if you have a problem with, let's say you imagine you have a problem with a unique solution, suppose Z was unique, then actually I can prove to you that any problem like that, where the solution is unique for a given instance, if you can solve it with a constant depth quantum circuit, you can also solve it with a constant depth classical circuit. So the fact that Z is not unique here is like essential, or else the whole thing wouldn't make any sense. We wouldn't be able to get this separation. So in particular, if you have, let's suppose that you have Z, Q of X is Z twice Z transpose X, for X in the kernel. Then I claim that I can take Z prime, which is Z plus Y, where Y is in the kernel of a perp. And this is also a solution. Okay, so this is like two lines using the same identity, mapping the XOR to mod to Z plus Y minus Z Y mod 4 and plug it in and you can see. Okay, so the point of saying that is like the set of solutions has the same size as the kernel of a perp. Okay? And now you ask, well, what are the solutions? I mean, I don't know the solutions. I don't have more intuition. Well, okay. Maybe I do have more intuition. Honestly, the simplest way to think about the solutions is to look at the quantum circuit that produces the uniform distribution over them. That's my best intuition.
There should be a formula for that depending on it, right?
Mm-hmm. Yeah, the formula is that you use linear algebra to find it. Well, if there was a very simple formula, then probably there would be a constant depth circuit. But
Not necessarily, there's going to be a subspace to one center from that. So it's going to be simple.
But this is the thing, is that the difficult thing is finding a base point for that subspace. It's like, obviously the kernel of A perp is the image of A, right? So this is easy. The hard part is finding one element. Okay, so this is how you hide a linear function in quadratic form. So the hidden linear function problem is given A, find the secret bit string or find one of them. Okay?
But even if you knew the kernel, right, and you wanted to do it for constant depth classical circuit, then you couldn't do it, right? So you need to use this large parity, which is quite low depth classical circuit anyway.
Even if you knew the
Even if you
kernel.
knew the kernel, this wasn't the secret, but nothing was the secret.
Mm-hmm.
The way you're asking to, I'm guessing something you're going to ask to sample something in this different subspace, right? Which if you want to do it in this way, you would say, well, choose an element in the image, or choose a random X and multiply with A, and this would require you to compute this many parities, but parities require a long depth circuit. I said it's not saying that the fact that this thing is hidden is important. It's not, I'm not sure it's important, but even if you know you want to compute two parities as well.
Maybe we could talk about it after. Yeah. Okay, so this is the hidden linear function problem to find the secret bit string or one of them, since there's many possible solutions. But actually, the problem that's going to separate the constant depth quantum and constant depth classical, we need to make a further restriction on the instances. We're going to have a sort of 2D structure, meaning if we view A as the adjacency matrix of a graph on n vertices, so like whenever there's a 1 on the off diagonal, that represents an edge between the two vertices. So if it's Aij is 1, that means there's an edge between vertices I and j. Then we're going to restrict to the case where this main input A describes a subgraph of a square grid. Okay? And that's just so that the quantum circuit that solves this problem becomes constant depth. It's kind of a technicality. You don't really need to think about this fact very much in the rest of the talk. Okay, so that's the 2D hidden linear function problem. And here's the quantum algorithm for it, and so let me now explain it. And I was going to go through the actual calculation. Well, anyways, so this is the algorithm. Here I don't need it to be the 2D hidden linear. This is just for the general hidden linear function problem. So at the top, You have the input register that just holds a computational basis state that specifies the matrix A. And everything is controlled on that register. So that register is just always in the state A. Okay? It never changes. It's just always in the state A, in the input and the output. But what's happening here is on the bottom we have a data register of n qubits. And it's very similar to the algorithms we talked about on Monday, right? We Hadamard everything. Then here what we're going to do is we're going to look at all the, if you think of A as describing a graph, so it's adjacent as the adjacency matrix of the graph, we look at all the off-diagonal matrix elements, like VW, or A is 1, so if A, VW is 1, and we apply a 2-qubit gate to any edge of this graph where that matrix element is 1, where the edge is present. Okay? So if we think of it as a graph, we apply this controlled Z gate, which is just a 4x4 matrix, 1, 1, 1, minus 1 on the diagonal. We apply that to all the edges of this graph. Then we look at the diagonal matrix elements, which are 1, and we apply a single qubit gate to all the qubits corresponding to those diagonal matrix elements. Okay? And then we Hadamard again, and then we measure, and we get some output Z, which is a random variable. And the claim is that the output is a uniformly random solution to this hidden linear function problem. Now, I would like to show you how this works. So let me try. And maybe we can, I think we started 5 minutes late, so maybe we can. First, let me just tell you the reason I want to show you why this works. I mean, it's just sort of a mechanical calculation, but the reason I want to show you is that it really is very similar to the Bernstein-Vazirani problem, even in the analysis. Okay, so I want to, because nothing is ever happening to this input register, I want to just look at what happens to the data register, okay? So I imagine that we fix the input A, and then we have some fixed circuit that depends on A happening here, okay? So I'm just going to look at the data register. And then I'm going to tell you the following fact, which is that this circuit that I wrote, if you just look at the data register, is equivalent to the following thing. So I'm just, bigger? So this is the measurement, okay. But you see what I did is, these gates, they're both diagonal in the Z basis. You see this is a diagonal gate in the computational basis, and so is this. So this whole transformation, the product of these guys, is just some diagonal matrix. And that's what I've written here as UQ. And this UQ, what is this diagonal matrix? It depends on A. Maybe I should call it UA. And what it does, it's not hard to show that it takes every basis state and maps it to I to the Q of X. Remember, Q is the quadratic form associated with A. So this is just like in Bernstein-Vazirani, where we have X going to -1 to the linear function of X. It's like, a direct analog of that. Now, so what do we have to do, to show this claim? Actually, I'm going to show a slightly weaker claim, because it's, so I'm going to show you that the output Z is a solution. I'm not going to show that it's uniformly random, okay? It's a little bit more involved to show that. But it's not hard, but it's more involved. Okay, so the claim is that the probability of Z is positive only if Z is a solution. And so P of Z, what is it? That we can write as A of Z squared, where A is the amplitude of Z, And that's given by the following expression. Okay, so, this is just, I apply the circuit to 0, I project onto Z, and then when I square that, I get the probability of measuring Z. Remember this? So this is now the thing we have to compute. And this thing, remember that if I had like an oracle here, a quantum oracle that computes a function, a Boolean function, what I would get is the Fourier transform. And here, actually, you get the same thing, except that, well, okay, I'll just show you the formula. This is straightforward calculation. Okay, so this is the, you just look at this circuit and compute the output state and project onto Z, and this is what you get. Okay, so it's like the Fourier transform of the function I to the Q of X, if you like. But now, now remember that at this point, if we were doing Bernstein-Vazirani, this would be -1 to the S dot X, and we would be done because this whole sum would just be 0 unless Z was equal to S, the secret. So we'd be done at this point. But in this case, we have to do a little bit more. We're going to choose a basis for the kernel of A. So let's write it as the span F1 through Fm, where these are bit strings and they span the kernel. And then we're going to extend that basis to a basis of 0, 1 to the n. So we're going to write 0, 1 to the n as the span of F1 through Fm, but then we're going to add more basis vectors completing. Okay.
Span of those two.
Yes, that's right. We're up to. Everything's not to. So then, the reason I was just to show you that this is, so 0, 1 to the n can be written in this way as the kernel of A plus some subspace L, and this is the thing which is spanned by Fm plus 1 by the remaining basis. Okay? Now, the point of that is what we're going to do is we're going to decompose this Fourier transform into a product of Fourier transforms, 1 over L and 1 over the kernel. Okay? And then what? Yeah, so let me do that. So I'm just going to continue this formula. So this is equal to m sum over, oh, I'm going where you can't see, is that right? Should I, can you see this? Yeah, okay. So W in kernel, so I'm going to write X as W plus V, where W is in kernel and V is in L. Okay. And then I have I to the Q of W plus V, and then I have -1 to the Z transpose V plus Z transpose W. Okay? But now we're going to use this lemma that I erased, which is that when W is in the kernel, Q of W plus V is Q of W plus Q of V mod 4. And since I have an I here, I can just plug in that formula because everything's mod 4. Okay? So that lets me rewrite this as 1 over 2 to the n. You see, once I get Q of W plus V is Q of W plus Q of V, now this breaks up into two sums. The sum over W and the sum over V can just be separated. So let me write that out here. This is, I think, going to be the last line on the right. Maybe I'll actually go up here. Okay, so I'm going to go up here. What I get is I get two Fourier transforms. I get the product. Okay, so here I use the fact that we proved earlier that Q of W plus V for W in the kernel is Q of W plus Q of V mod 4. So now we have just a product of two things. And we're trying to show that this is 0 only if Z is a solution. So it suffices to show, let's see if I want to show. Yeah, so we're going to show that this is 0 unless Z is a solution. Okay? We're going to forget about this term, and we're going to show that this term is 0 unless Z is a solution to this HLF problem. And so, how can we simplify this term? Who can tell me? Almost done. So we have Q of W on the kernel of A. That's not.
It's a linear function.
Right, so it becomes a linear function. This thing. So now we really have Bernstein-Vazirani just appearing in this chart. So this is S dot W, where S is the sequence string. Okay, so now you know what this sum is, right? Well, okay, maybe you don't, but let me just tell you that it's not hard to show that this is 0. Well, I'll write it this way, unless Z is equal to S plus Y, where Y is in kernel of A first. Okay, so there's like a little bit of, this is just some algebra fact for Fourier transforms. But remember we showed that the set of solutions is this set. You take one solution and you add an element of kernel of A first. So this shows that this whole expression, the probability, is 0 unless Z is a solution. So that's sufficient to show that you only ever get solutions from this circuit, and one can do more calculation and using a few properties of quadratic form, you can show that actually you get a uniform distribution of solutions. Okay, so we have about 10 minutes left. Yeah?
So what if you try to just sample a uniform element in the kernel of A? So you have matrix A and sample a uniform element there. So can you do it with quantum circuit?
Well, I would be much happier if I could do that, because that is a linear algebra task that is very common and that you want to do quite frequently. Whereas this one is not so common, and we don't know how to relate the two. I mean, it's somehow, we spent quite a bit of time thinking about the relationship between these things. So the short answer to your question is no, I don't know how to do that.
You also don't know who is impossible.
That's right. Yeah, I think if you have a sparse matrix A, like in the 2D case, then classically you can do it in time n squared. It's to sample a random Z in the kernel using sparse linear algebra tricks with some standard algebra. Yeah, I don't know. Okay, so this is the algorithm, and it's very similar to Bernstein-Vazirani, and somehow like inside it is Bernstein-Vazirani. And I want to show you. So this is the algorithm which solves the problem in general, but I claim that when you restrict to this 2D set of instances, then the algorithm has constant depth. And so I just want to show you how that works. So I want to imagine, I'm imagining these are my qubits, and I have one at every vertex of this 2D grid, okay? So then the input A, this matrix, I can represent as a set of edges and dots on this grid, where an edge is an off-diagonal matrix element of A. So the red shows the adjacency matrix of the graph that A describes, and the green are like the diagonal matrix elements, okay? So this is just representing the matrix A, and then what do you do in this algorithm? I want to show you that it's constant depth. So you apply Hadamard's everywhere, that's one layer. the next thing you have to do is apply controlled Z's everywhere there's a red edge. Okay, but because it's in 2D, you can do like the odd horizontal edges, the even horizontal edges, the even vertical edges, and then the odd vertical edges. So you just do them in 4 layers to cover all the red edges. Then you apply these single cubic gates to all the green ones, then you have them hard, and then you render them. So it's all constant depth in 2 dimensions. Okay, so I mean, somehow all of this was described in the algorithm, but what makes it more interesting is that you can't do this classically with in the following sense. So imagine that you have, I didn't really talk very much about the kinds of classical constant depth circuits we're comparing against, so that this is my opportunity to do that. So we are going to be talking about classical circuits where all the gates have a constant number of inputs. Okay? We're allowing them to fan out, meaning that once you compute the function computed by the gate, you can fan it out and put it as the input to many other places, but we restrict the fan in to be constant. Okay, so this is a circuit family known as NC0. But we're actually augmenting NC0 because we're going to allow it to have random input bits, and we're going to allow those input bits to be drawn from any joint distribution. And so what we prove is that any probabilistic classical circuit from this family that solves this problem with probability greater than 7/8 in all instances has depth scaling logarithmically with the input size, so it's increasing. So in other words, like just in pictures, if you have a circuit from this family, so it's constant fan-in gates, and it takes the input and it takes some random bits, and it produces an output with probability 7/8, then the circuit has to have logarithmic depth. Okay, so now in the last 5 minutes, I would like to tell you about how we proved this. And the proof ideas actually are directly related to the sorts of things Thomas was talking about in the last lecture. So, the fact that you can win a game using entangled resource state, but you can't win it with shared randomness, that's sort of known as quantum non-locality. That measurement statistics of entangled states can't be reproduced by local invariant models. That's how the physicists would describe this, and I'll say a little bit more about this in a moment. But classical circuits that are shallow, constant depth say, they are sort of fundamentally local things because, it's a simple fact that every output bit of such a circuit depends only on a constant number of input bits. Okay, so I'm going to come back to the slide in a moment, and I hope that after, when we come back to it, you'll understand this better. I think now it's maybe a little bit confusing. But I want to just state this, and then we'll state it again later. So the point is that the shallow classical circuits are a generalization of like classical strategies for games, like local invariable models. And the outputs of constant depth quantum circuits have a strong version of quantum non-locality. So it's like even if you have it's like you can have a game where even the resource state is generated by a constant depth quantum circuit. This resource state, you should think of the output as being like the players of the game. And so like even the resource state is generated by a constant depth circuit, quantum circuit, and that can be with that shared resource state they can be classical players using a classical constant depth circuit. Okay, that probably wasn't completely clear. So I wanted to take another game which I don't think we've discussed in this course, and I want to phrase it in the language of circuits so that you can sort of understand the analogy. And so this is just like the magic square game, because the quantum is going to be able to win with probability 1, but I'm going to phrase it in the circuit language. So actually I wanted to start by talking about the classical players in this game. So, but I'm going to view it as a classical circuit. Okay? So this is called the GHC game, if you like, which dates back to 1990. Riedenberger, Horn, and Zappinger, and Norman studied this game. So a completely local classical circuit, what do I mean by that? I just mean that, let's say there's 3 input bits, and let's say in this example that I want the outputs to be plus or minus 1 bits. Okay, so I have 3 input bits, I have 3 outputs, and the outputs are just computed completely locally from their input bit. So this is what I would call completely local. This, every output bit depends on only one input bit. So these functions are just functions of that one bit. But I could also have a probabilistic classical circuit. So So you should think of this as being like shared randomness. So now I would call this a completely local probabilistic circuit when they share a random string. So now the function takes as input, each of these functions takes as input their input bit as well as the random string that's shared. Okay? And this is what would be called the local invariable model. This is like a classical strategy for a game, if you like. So this is the input-output relation that characterizes this is like how you win the GHC game. Okay, so the GHC game, we only care about input bits that sum to 0 mod 2, okay? So there's only 4 configurations. And we always want the product of the output variables, Z1, Z2, Z3. So if all the input bits are 0, we want it to be 1, and in all other cases where these sum to 0 mod 2, we want it to be -1, okay? So there's just this little table. So this is a game. But I want to think about it as a relation. Like, imagine that I have a circuit, and I want it to have this input-output relationship. If I get input bits B1, B2, B3 that are all 0, I want the product of the output bits to be 1. That's a relationship between input and output. Okay, so actually, so it's a fact that you can't realize this input-output relationship by a probabilistic classical circuit. It's not hard to show. So we'll call this the GHC relation. But if you take this entangled state, this 3-qubit state, which is the cat state on 3 qubits, or the GHC state, and you allow players to share that state, and now you have a quantum circuit which has exactly the same structure. These unitaries just rotate to different bases single qubit bases depending on the input. So this is if you choose these unitaries appropriately, then you can win with probability 1. So in other words, this quantum circuit, which has the same structure as the classical circuit, can actually produce this input-output relation. Okay, so now, so this is just the motivating example, and I'm not really going to show you the details of what we do, but somehow the way to think about it is that the problem with this, the reason why this is not really what we want, is that you have to start with, well, there's 2 things. One is that we're restricting the classical circuit to be this completely local thing, and ultimately we care about constant depth classical circuits. So we want to allow like a generalization of local invariable models, which allow sort of constant depth circuits instead of completely local circuits. So that's one thing that's not quite right about this. The second thing that's not quite right about this is that here we started with this resource state that's some entangled state, but in our case we want to start with like just an input string. And so any resource state has to be generated by the constant depth quantum circuit. So we want to allow constant depth in both classical and quantum settings, and in the quantum case we want the resource state to be itself generated by the constant depth circuit. And actually that's sort of like exactly how our analysis goes, as we sort of, the way that we prove the separation involves embedding a game into this constant depth circuit and viewing the quantum algorithm as performing one of these Bell experiments and so on. Okay, so there's the slide. For shallow circuits, generalize completely local circuits or local invariable models, and the outputs of constant depth quantum circuits have this strong version of quantum non-locality that can be constant depth classical circuits. Okay, so what else can we do with constant depth quantum circuits? So that's an interesting research area. And we're going to learn about, I mentioned already this Terhal-DiVincenzo result, which was sort of a very fundamental result showing that you can't exactly classically sample from the output distributions, and we'll talk more about that this afternoon. But, it would be interesting to know, there are other problems, other relation problems, or other tasks that can be done with constant depth quantum circuits. So I'm going to end there. And if there are questions, let me know.
I have a question. So, this is an example where you mentioned something very useful with this quantum depth circuit.
Well, useful is a strong term.
Useful-ish. And it's classical, right? But you have going for classical constant depth circuits that we've developed in a complexity, a bunch of techniques to low bound, right? Very things you cannot So are these techniques also for the quantum circuits?
No. Actually, I think you know of this technique by Viola, and maybe you were involved, having to do with the decomposing the output distribution of an MC0 circuit with random input bits as this convex combination of bit block sources with comparable mean entropy. And it was, yeah. So we actually played a lot with that because originally we were trying to use that as a proof technique. So we don't know if that holds in the quantum case. Actually, that would.
But Endanaro used these techniques to show lower bounds.
Who did?
Endanaro,
Okay.
in their proofs of the lower bounds for surfaces. They use, so you can extend those techniques to show some lower bounds for one surface.
So really, you're talking about the bit block source.
I'm sorry.
Which techniques are you talking?
They basically took the lower bounds technique using expansion of the expansion of the probability distribution that is an output of.
But I think we may be talking about either there's a relationship between what I'm talking about and you're talking about that I don't understand, or we might be talking about different field results. Because, well, maybe we can talk about it afterwards. Yes.
Do you have a rough estimate on what set settings are for current machines?
No. We can talk about it later.
Is the lower bound tight for classical circuits? Log n? Is there a log n that classical circuit that does it log n?
I don't know. Okay, let's have lunch.